In this lecture, I would be talking about stereochemistry with carbohydrate molecules and some very important terminologies like epimerism and anomerism. Okay, so let's first start with epimers. What are epimers? Two stereoisomers are epimers when they differ in configuration about only one chiral carbon. So let's take an example. Suppose this family of D aldoses and let's come to aldohexoses like these guys here with 6 carbons 1, 2, 3, 4, 5, 6, 7 and 8. And the most important here is D-glucose, this one. And if you compare D-glucose and D-mannose, this whole family has already been explained in the last lecture. So if you don't know, if you are not aware of these things, then you can go back to the previous lecture. But now if you see that D-glucose and D-mannose, they have the same structure, of course, they have the same formula, they are isomers. They are not even structural isomers, they are stereoisomers. What is different between D-glucose and D-mannose is like if you start checking the Fischer projection, this carbon here, the C2, right? According to IUPAC numbering, the topmost carbon, that of the aldehyde group, is C1 and that carbon is C2. So on the C2 you have a different configuration of chiral carbon, right? So glucose and mannose are C2 epimers because the configuration at C2 is different. Similarly, if you check glucose and galactose, so let's check again glucose and galactose. Let's start checking from the first carbon. C1 is not chiral, CHO is not chiral. Then you go down, this C2 has the same configuration, C3 also has the same configuration. It's the C4 where the configuration is different, and it's only the C4 because C5 again it has the same configuration. So D-glucose and D-galactose are C4 epimers. So one might be thinking why we are using this kind of terminology, epimerism, why we are using this epimerism, because you should understand that when this whole family of aldoses and ketoses were realized, then at that time the most important one here, like in this family, the most important one is glucose. So if we know that mannose is C2 epimer of glucose, we can easily understand what mannose is. And if we say like D-glucose is C4 epimer of D-galactose is C4 epimer of D-glucose, so we can, with respect to D-glucose, we can very easily determine other configurations if we know these epimerism kind of a relationship between something and the D-glucose. And for that you need to understand what D-glucose is, what is the configuration of D-glucose, like you need to know the Fischer projection of D-glucose. So that's very simple to memorize, because in D-glucose you have 4 chiral carbons, right? Last carbon is not chiral, you have, and the first carbon is not chiral. In between you have 4 chiral carbons. This is C1, this is C2, C3, C4, C5. So because it's D-glucose, so the last OH is at the right, and all other OHs are also at the right except for the C3, except for the OH at C3. So this is how you can remember D-glucose. You should remember that it's the C3 where it is different, where the OH is on the left. On all other carbons, the OH is at the right. So if you remember the configuration of glucose then, and you know some epimer relationships, like if you know that D-mannose is C2 epimer of D-glucose, then you can easily just reverse this OH to this side and you can get D-mannose. So it's a very convenient method. Okay. So which one is the C3 epimer of D-glucose? You see, so just now we saw that it's the C3 where the glucose molecule, the OH of the glucose molecule is on the left, right? So if you take the C3 epimer of D-glucose, all the OH will be aligned on the right. And what is that molecule? That molecule is not so common, that aldohexose is not so common, but this one right here, this D-allose, is that molecule. Allose, I haven't seen it like anywhere else except from this table, but good to know, it's D-allose. So yeah, to memorize the configuration of D-glucose, the Fischer projection of D-glucose, and then using epimerism, it will be very easy to determine some other structures. Now let's see, what about which of the following should be L-glucose? Well, so these are the options. You know what D-glucose is, right? We discussed just now, we discussed that D-glucose is something like this: 1, 2, 3. At the third carbon, the OH is at the left, otherwise all other OHs are on the right. This is D-glucose. And when you have to think about L-glucose, a lot of students, a lot of people, they try to think that because we have to make L-glucose here, and in the L family, the last OH is on the left. So what they do is they pick up this option because they compare it from D-glucose and they say that we have to only reverse the OH at the last carbon, but this is not right. This is not right because L-glucose is not the C5 epimer of D-glucose. Because when you make an epimer, you are making a diastereomer. You are keeping all other configurations same and you are changing just one configuration. And diastereomers are basically quite different from each other because they have different dipole moments. For example, this one is of course D-glucose, and suppose we are the leading scientists and we have to decide how to which compound should we take as L-glucose. Even if we know a little bit about the properties of optical isomers, then we would say that we would not like to take this molecule as L-glucose because this will be very different from D-glucose, because these two are diastereomers, because the dipole moment here, so suppose these arrows here, these OH groups, they will withdraw electrons. Okay, so these arrows are here, OH, one arrow is on this side and the other arrow is on this side and the other arrow is on this side. So you have three arrows on the same direction in the Fischer projection. I know that this is not the exact 3D representation, but you will get a feeling of that, of the actual molecule from here. So you see that three arrows are on one side and one arrow is on the other side. The polarities which are being which are present in this molecule because of these OH groups. And here you see in L-glucose, if you see this OH is here, one arrow is here, one arrow is here, one arrow is here, and the other arrow is like towards left, right. And here you see that the dipole moment would be different. So this molecule would have a different dipole moment, and this happens with diastereomers. So this C5 epimer of, this is the C5 epimer of D-glucose. This is a diastereomer of D-glucose, and we would not like to take it as L-glucose. Rather, we would like to take the complete mirror image, and in that complete mirror image, the OH will be, the last OH will be at the left, and all other OHs will also be reversed. All other configurations will also be reversed. So now, if you think in terms of dipole moment, one arrow is towards this, the other arrow is towards this, and this, and this. This is very much like glucose. It's just the mirror image of D-glucose molecule, and this is very similar to D-glucose. For example, the mirror image of U would be much more simpler than the half mirror image of U. So this enantiomer is taken as L-glucose. Okay, the enantiomer, this one is the right answer. C is the right answer. So remember, epimers are diastereomers which will have different physical properties. It's more reasonable to take enantiomer of D-glucose as L-glucose. Okay, then the C, then you might ask, what is this? What is the name of C5 epimer of D-glucose? It's not a very common carbohydrate molecule. I will give you some option and you can work it out by eliminating the reasonable ones. But you can see that it cannot be L-glucose. It cannot be L-galactose also, because galactose is, so D-galactose. D-galactose is C2 epimer, sorry, C4 epimer of D-glucose, right? So here you have the option L-galactose. So L-galactose. So what about L-galactose? How would it relate to D-glucose? So if you see these carbons C2, C3, C4 and C5, and in comparison to D-glucose, if you check D-galactose, then C2 will be matching, C3 will be matching, C4 will not be matching, and C5 will be matching. The configurations, I'm talking about the configuration of chiral carbons. So the C4 of D-galactose would not be matching with D-glucose. So if we reverse all of them and you are thinking about L-galactose now, so in L-galactose, now in comparison to D-glucose, the C2 will not be matching, right? The C3 will not be matching, the C4 will be matching, and the C5 will not be matching, right? So if you take L-galactose and if you compare it with D-glucose, there are many things which are not matching. It's not only the C5, but there are many chiral carbons whose configurations will not be matching. So it's not D-glucose. Similarly, you can check for L-mannose, it would not be that. The answer here is L-idose, but it's not a very common carbohydrate. So epimers differ in configuration at about only one chiral carbon. Okay, so the modern terminology is diastereomers and enantiomers. Epimer was used before, I think, and also it's also used nowadays also, because I like this idea of epimerism, because it centers the whole attention towards glucose and you start to see all other molecules from glucose. So it's a very convenient convention. Then there is this interesting question: are all epimers diastereomers? Not so, because if there is only one chiral carbon in a molecule, in a sugar molecule, and we have to take the epimer of that, then we will have to make an enantiomer, because there is only one chiral carbon, right? So yeah, but if there are multiple chiral carbons, then you are inverting the configuration of only one chiral carbon, and then you will get a diastereomer for sure. Okay, so not all epimers are diastereomers. Let's think about this question now. D-glucose and D-fructose are, well, where did it come from? Let's see, what are the options? Diastereomers, enantiomers, epimers, and structural isomers. Well, this is very simple, because D-glucose and D-fructose, if you remember, if you have seen the last lecture, you know about D-fructose, and even if you don't know about this D-glucose and this D here, if you remove that and you're just thinking about the structure of glucose and fructose, you will see that the structure of fructose is different. It has a ketone group, so they are structural isomers. Anyways, I think this question is here to make you realize something else, and that thing is, like, if you take D-glucose and you take D-fructose, from bottom 4 carbons, like the bottom 4 carbons, they are exactly the same. So the last three chiral carbons are exactly the same. So in this lecture we talked about D-glucose, like you have to memorize this configuration of D-glucose, the Fischer projection of D-glucose. And how do you do that? So you know that at C3 things are different. So at C3 this OH is different. All other OHs are at the right. At C3 the OH is at the left. So if you have to make D-fructose, it's again the same rule. At C3 things are different. Here you have one less chiral carbon, because the C2 also is not chiral, C1 is not chiral, C2 is not chiral, C6 is not chiral, and C3, C4, C5 are chiral, and it's at the C3 where the OH is not on the right. Because it's a D fructose, the last OH, this one is on the right. So this the OH at C5 is on the right, C4 is on the right, but not at C3. So again, it's the C3 which matters, right? This way you can remember both the Fischer projections. Okay, so let's let's summarize a little bit. You like when we are young, we know this formula, which is for glucose and fructose. But this formula is not only for glucose and fructose. This is for many other molecules like galactose and mannose. And as we studied, that like the D-glucose can exist in two forms. The glucose can exist in two forms, D and L forms, and these forms are enantiomers. They are not epimers; they are enantiomers. And there is no new term for enantiomers because enantiomers are very special. So enantiomers are still enantiomers, like mirror images. But in diastereomerism, we have a special class of epimers. Okay, so now the D-glucose can also go into the cyclic form. So this is not the end of the story. The D-glucose can attain cyclic form, and it could make a 5-membered ring or a 6-membered ring like pyran and furan. And there would be no double bonds though, because these double bonds will not be there in this kind of cyclic molecules, but the names are still derived from pyran and furan. So if the D-glucose goes into 6-membered ring, it would be the 6-membered ring would be called pyranose ring, and the 5-membered ring would be called furanose ring. And why this happens? Because in glucose molecule you have CHO at the first carbon and you have many other OH groups, right? And these OH groups can attack on the CHO. This because it has lone pairs, oxygen has lone pair, and this CH group, it has a carbonyl group and it has delta positive charge, and this can act as nucleophile. So there could be nucleophilic addition reaction leading to formation of hemiacetals. So because of that kind of a possible reaction, and that reaction is possible inside the molecule itself. So if you give it room, if you dissolve the molecule in water and give them room, they can react, they will react and form 6 or 5-membered rings, because these are good size for rings. So when the 6-membered ring is formed, or even if 5-membered rings are formed, this can happen in two ways, and one of the D-glucose would be called alpha D-glucopyranose. When it forms 6-membered ring, it's pyranose, and there is a symbol more alpha. And because we started from D-glucose, so that's why we have D-glucopyranose. So we have D-glucopyranose. It means that you are starting from D-glucose, you are going into a pyranose form, but there is something which is indicating alpha. What is that alpha? We would see. This can only be understood if you understand the attack, if you understand the formation of hemiacetal. And then there could be the other form beta, and it would also be called D-glucopyranose. There in two ways 6-membered rings can be formed, and similarly the furanose, it can also be formed in two ways. Okay, so it's not that complicated, is it? Like everything, we have a proper explanation for everything. So it might look a little bit complicated, but it's not. After a while, if you understand all these ideas, then it's not difficult to memorize these things. Like I don't myself personally, I don't like to memorize anything at all. What does alpha and beta signify? Yes, what does alpha and beta signify? Let's see. This is going to be very interesting. You have a D-glucose molecule right here, and you are thinking how it could cyclize, how it could go into the ring form. So it has a lot of OH groups, right? And you are thinking which OH group can attack. The first OH group is too close. You will get a 3-membered ring from this attack. The second one is also very close, this one. You will get a 4-membered ring. From here you can get 5-membered ring, and from how do I say 5-membered ring? Because you see, this is the oxygen atom which will definitely be combined. What kind of attack is happening here? First of all, so you have an OH and there is a lone pair, and these things can be connected. this is going to attack here. This lone pair will move on the oxygen, and this hydrogen from here will transfer back, right? So you will get COH, and this O will connect itself to the C. Which O? This O here will connect itself to the C, and this H will reach here, or maybe some other H from the solvent, but the ring will be formed due to the oxygen, the attacking oxygen linking to the carbon of the carbonyl group. So suppose if you are attacking this oxygen and you are joining this to this carbon, so you have two members already. Member number one is this oxygen and the other is this carbon. So two members, three members, four members, five members, right? So you will get a 5-membered ring. But if you attack from this lower oxygen, this oxygen will give you a 6-membered ring, because this will connect to this now. So two members already, 3, 4, 5, 6. And the last OH is too far. 7-membered rings are not so good. So once you understand this, then which one should we prefer? Which one should we prefer? So it has been known by scientists that the D-glucose, it likes to go in the 6-membered ring. What is the reason behind it? It's no, I'm not sure. Maybe it's very intricate. It's an intricate work of nature, but it likes to go in 6-membered ring, because in any polymer of D-glucose, if you see, you will get these 6-membered rings. So let's see what happens when it goes into 6-membered ring. Glucose is found to exist in pyranose form mostly, hence we are going for a 6-membered ring attack. So if you understand this attack, then you can go for the furanose form also and think about that also. So there's nothing to memorize here. So what is happening here? You see this arrow coming from nowhere. This is from where the molecule turns, okay? And none of the configurations will be disturbed. This configuration, this configuration, this configuration. You can determine the absolute configurations also, like whether this is R or S. None of these configurations will be disturbed during the attack, because the attack is happening on this carbon atom, and when this carbon atom is attached, it was not chiral before, and when this oxygen attacks, so you can see that this group will change, this oxygen will change into OH group afterwards. So you will have, on this carbon you will have an H already, and then now after the attack there will be an OH, and there will be a ring which is connected from O side, and from here there is another C. So all the 4 connections to this carbon will become different, and you will get a new chiral carbon. Crazy. You already had 4 chiral carbons, and now you get 5 chiral carbons after the attack. And this attack can happen from both the sides, right? Because this aldehyde group C double bond OH, this group is planar because of sp2 hybridization, and the attacking lone pair, the oxygen which is coming and is going to attack through its lone pair. It can attack from above the plane or down the plane, and you will get both the configurations. So this carbon becomes really important, the carbon of the aldehyde group. This is called anomeric carbon, a new term, anomeric carbon. This is very important, stereochemically speaking, anomeric carbon. So we've got a new term, anomeric carbon. Okay, fine. These names will help us to understand the structures of coming molecules. So this carbon will get chiral after the attack. Depending upon what configuration it takes, we will decide alpha and beta, okay? But we wouldn't be seeing R and S configurations. We will be deciding in a very different way. So let's go, because R and S nomenclature, I think it came after all of these things was done. Like Fischer got his Nobel Prize for synthesizing sugar molecule, I think, and at that time I don't think R and S nomenclature was being used. That's why the theory is a little bit classical in a way, and much more juicy, much more uh, interesting in a way, because when you logically put things into boxes, then it becomes a little bit mundane. Anyway, so for simplicity, we will show the molecule in Hayward projection. It's a kind of projection because when the attack will happen, you can't use Fischer projection now because the molecule will be cyclic, and there is no way to represent Fischer projection in cyclic form. So we will use Hayward projection. What are the ideas behind Hayward projection? Let's see. So you will have to make this oxygen here and the anomeric carbon here, because most people are right-handed, and the first carbon which you want them to notice is this carbon, so you would like to have it on the right here, right? This is the special carbon. This point is special in this molecule. So this anomeric carbon will be here. Which one is anomeric carbon? C1. So let's do the IUPAC numbering: 1, 2, 3, 4, 5, and 6. So C1 is here, and this O, what is this O? This O is coming from here, right? This O is getting itself into the ring, so this O is coming from C5. So this C5 is here. So what are these? So these are 4, of course, 3 and 2. And now, very interesting thing, at C5, the CH2OH group is written up, and I read it somewhere in some textbook that the CH2OH is written up because of convention. But then I don't think it's because of convention. It's because of this configuration. Let me show you how. So I will use absolute configuration now, RNS. So take a look at this. This thing right here, this is the 4th priority. We are talking about C5 and we are deciding the priorities, and then we will decide whether it's R or S. So hydrogen is of course the 4th priority. The first priority is this OH because oxygen has the highest atomic number. Then these groups, this is connected to a C, this is connected to a C. So first connection we have a tie. In second connection you have O and C and H here, and in second connection you have H, H, 2H and an O. So you see that the above one is more important. So that's why we will give it a 3, 2, we will give it a 2, and we will give it this thing a 3. So 1 to 2 to 3, you will trace that path, and that path turns out to be anti-clockwise, but the hydrogen is coming towards you. The 4th priority is coming towards you. So according to IUPAC nomenclature, it should not be written S. You normally go anti-clockwise, you take S, but here you will not take S, you will take an R. Okay. So this C5, when the attack happens, the C5, the configuration of C5 is not going to change, right? And the C5 should be in R because there's nothing happening at this carbon. All of the molecule is twisting, and if you exchange bonds, then only the configuration will change. So this R will remain R, and for this thing to remain R, you need to have the CH2OH up here and the H down here. I can prove it to you because this should be R. In this way it should be R. So you can see the first connection is still this O, so this is first priority, and the second hydrogen is the 4th priority, and the second priority is here just like before, and this is the 3rd priority. Pause it if you want to ponder on it. So this is the carbon, and if you look from above, from this side, hydrogen will be away from you, and 1 to 2 to 3, you will see this is clockwise, right? So I haven't explained the rules of determining R and S still not on my channel, but very soon I will put a video. So if you are stuck here, then you can go back and see that video and think about that, or you can find this kind of a video very easily on YouTube, how to determine R and S. But yeah, the point is that this CH2OH is up here not because of the convention. There is a proper reason to that. Why? How do I know this? Because yesterday I was recording this same lecture and I said that this CH2OH was there because of convention, and then I stopped my recording to think, really, is it convention? And it turned out that it was not. So still learning. So yeah, let's see, the CH2OH is up here, and so the C6 is here, right? And then what happens now? This molecule twists from here. So these two H, which seems to be on the same side, which like very close by. Now these two H will not be very close by. So this H is here. So then the other H. Okay, so this is about the other part, but concentrate here. So now you will see that, yeah, these two H, these hydrogens will differ. So if you have a CH2OH up here, down below you should have an H here, and the other H at C4 should be here. And you can cross check by absolute configurations that the configurations are not changing. So yeah, so then this is because of the twist. Notice the twist. These two OH are now separated. They were close by here. Okay, and then what happens? OH is of course down there, this OH, and then afterwards there is no twist. So this H we wrote here, and then this H will be opposite from that H, and the OH will also, these OH will also be opposite. So that's why you have these things here. So we are concentrating on the OH at the fourth carbon. At the fourth carbon, 1, 2, 3, 4. This OH is here. So at the third carbon, you will have an OH away from that, and at the second carbon you will have an OH away from that. So from fourth to third you have away, and you still have these OH group away from each other. And C1, it could happen in any ways, because this is the carbon which have been attacked, and according to attack it could be that like the OH can be here also or here also. So it depends which side, and that's why we have alpha or beta, not on the both side, but yeah, it depends. So same situation in the other molecule till here, same story, but now this last H, you see this OH is here up at the first carbon, and this OH is down at the first carbon, and now we need to use alpha or beta. So I don't like to memorize things. So how do I memorize which one is going to be beta? Because one thing I know is that beta glucose is a stable form. Beta D-glucopyranose is the stable form, because you will see it in cellulose, and you will see it in cellulose, yes. So cellulose is the principal structural form of one of the very important structural kind of a carbohydrate, which provides structure to plants. So it's present in the cell wall of the plants, and it's a very stable molecule. And its stability is because you saw these OH groups separating, right? This one is away from this one is away from this, and if you notice the CH2OH group also is away from this OH here. So right now you are having all these groups in trans fashion, away, 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 and then if you continue this fashion, you will get a very stable molecule, and I am pretty sure this one is going to be beta. And this one is going to be alpha, because it's not that stable. You have this bigger groups away, 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 but now they are matching. So I am pretty sure the first one is beta. So OH is pointing down, you have an alpha. Then you make it like as a rule for the upcoming molecules, that if the OH will be pointing down, so you will have alpha. You will say that this is alpha. And if the OH is pointing up in the Hayward projection, of course, because there is no up and there is no down, unless and until you have decided a few rules. So if the OH is pointing up in the Hayward projection, then you get a beta molecule. Okay. So yeah, this statement here is about beta D-glucopyranose being the most stable form of D-glucose. Yeah, so I already told this story. I made this presentation a little while ago, so I don't know what's going to come next. It's very less torsional strain. Torsional strain, what is torsional strain? We can go on discussing about that, but it's related to steric hindrance. Very stable molecule, beta D-glucopyranose. Notice the bigger groups are all opposite to each other. Alpha D-glucose. Now comes the interesting question. Beta D-glucopyranose and alpha D-glucopyranose are, and you have these options: stereoisomers, enantiomers, diastereomers, tautomers, epimers, and anomers. Oh my god, this is very interesting. I always surprise myself. So, good options. Stereoisomers, they have to be stereoisomers because they have the same structure, right? They have the same formula, C6H12O6. Nothing was lost during the attack. Only the hydrogen transferred from one carbon, one oxygen to the other oxygen. There was no loss and no gain of any atom. So C6, the formula is same. The structure is same, isn't it? All the atoms are connected to the same kind of atoms. Structure is same. It's only that something is up and something is down. So it's only, there is only stereo difference between these two molecules. So they have to be stereoisomers. And enantiomers, they are not enantiomers for sure, because they are differing at only one, this carbon number 1, the anomeric carbon. They differ in configuration. If they would have been enantiomer, all the configurations would have been reversed, right? So they are not enantiomers. This is wrong. They are diastereomers for sure, because they are stereoisomers, and if two stereoisomers are not enantiomers, they are of course diastereomers. I think that's a definition of that should be the definition of stereoisomer. Anyways, and tautomers. Whoa, tautomers are those kind of isomers which can exist. Like if you take one of them and they can interconvert, in the they can interconvert among themselves. And it can happen because if you know about this meter rotation of glucose, if you take one of these molecule, they will open up to D-glucose, and they might cyclize in a different way and reach there. So they are in equilibrium with each other in solution. So I would like to call them tautomers. So stereoisomers, not enantiomers, diastereomers, and tautomers. And epimers, yes, they are epimers for sure, because they differ. They are diastereomers and they're very special. They differ in configuration about only one carbon atom, and that is that anomeric carbon which we talked about, epimers. And last, anomers. Damn, this is what, suppose this is a single choice question. So currently it's like a multiple choice question. Suppose it would have been a single choice question, then it would have been wrong first of all. But still I am saying that the best option here is anomers, because this is to represent this kind of stereoisomerism. We have specially made this term anomers. When some glucose molecule, when some a carbohydrate molecule is cyclizing, and there is an anomeric carbon, and you get two different stereoisomers differing in configuration only about that anomeric carbon, and you call these two isomers anomers. So this is the best option here. There's nothing best, of course, but this is just to make you understand the importance of the history of this word anomerism, the logical history, I would say, because I don't know much about the scientific history, how all these things were being imagined. So yeah, well, there is a not on tautomers. So this I would like to tell. I remember, like, I have a faint memory that I was thinking about this, whether to call this tautomer or not, and we can call these tautomers because they can interconvert among themselves through glucose. So it's not that they are interconverting and there is another molecule in between. So I would like to call them tautomers and anomers for sure. This is very nice. This is new term which we define here, anomers. Which of these two forms you expect to have higher melting point? Which of these two glucose forms would you like to think that they have higher melting point. How would you decide that? This is again a very interesting question. So if you think about these dipole moments, see, melting point. Okay, melting point has more to do with symmetry of the molecule also. So it seems like that the beta form is more symmetric and it can fit better because these bigger groups are alternate to each other. So it's not completely symmetric because of this CH2OH, but it feels like it's more symmetric and it will fit much better in the lattice. So this is me asking question to myself, the past me asking to myself. And I think I would like to go with the beta form. Yeah, I would like to go with the beta form because all of the things are almost similar. Whoa. Yeah, so the alpha form of glucose has melting point 419 and the beta form 423. Oh, 4 kelvins. It's just a minor difference. Interesting. So I think, yeah, this is it for this lecture. And thank you for watching. I enjoy making these videos. Thank you.